Hi there. This lecture video is a supplementary discussion of short transmission line modeling that we had in the past. And this will specifically show how VS or sending voltage parameter is derived. Okay, so let's start off with using the phasor diagram of a lagging power factor load here. Okay, and we just have to rotate this, okay, for easier analysis. You can see there. Okay, you just have to recall how to find a resultant vector. Okay, and that is simply the resultant vector that we have here is Vs, obviously. So we just have to get the square of the x components and the y components. All of them are summation. Okay, summation Vsx and summation Vsy. Okay, so how do we get that? So first, we have the VR component. We get its x and y respectively. It's VR cosine theta r and VR sine theta r. Okay, next one, the IR thing there. We have to get the IR is simply the x component. There's no y component. And then for IX, no x. Alright? Okay, so given all that, we get the summation of VSX as VR cosine theta r and IR. Okay, for summation of VSY, it's VR sine theta r plus IX. Okay, so given those summation, we have now VS squared. Okay, now this is just the same thing, no? I just made use of the notation absolute so we can differentiate VR from a magnitude and the one that it's vector. But here we refer to the magnitude Vs, VR, INR. Okay, so please don't get confused. Now going back, we have that Vs equation now here. So well, we have to expand it, the square. All right, we have to square those, and it's given here. Okay, VR squared plus I squared, R squared plus X squared, etc. Alright, now this parameter, this term, I mean, I squared, R squared plus X squared, is usually of negligible order. Okay, so that the VS now becomes simply like this. Okay, we have to expand that binomially and retain the first order only, so we get here. Vs is the approximately is VR plus I, etc. Okay, thus take note that this is just an approximate expression, especially or specifically for lagging power factor. Now for leading power factor, this is the approximate expression. Okay, all right. On the other way around, we can make use of phasors in the complex notation Vs, Vr, I, and Z. Okay, so I made use of the arrow bracket or something like arrow there to notate that it is a vector. Okay, so the Vr there is given as Vr plus J0. Okay, the imaginary and real components for I is I cosine theta r minus J sine theta r, right? Because this is lagging. For Z, it's R plus JXL. So we have given all these real and imaginary components of those vectors. So we insert that in VS, vector VS. Okay, so simplifying that, we get VR and then IR cosine theta r, IR cosine theta r, and then the I cosine theta r, then JXL. Alright, and the next term is I cosine theta r, I negative J sine theta r, and then lastly I negative J sine theta r times JXL. So we have J squared IXL sine theta r. Okay, so the J squared there will definitely be equal to -1. -1 times negative is positive. So we have to just group the real part and the imaginary part. So here it is. This is the real part and this is the imaginary term. Okay, now let's go back. So this is the real and imaginary. So applying here, we can make use of, because this one is complex. Now in order to simplify it, all our vectors there, especially the vs there, becomes, in getting the magnitude, we have vs squared equals the square of that term plus the square of another term. Okay, now this term is quite small, so according to references, it can be neglected. That's why we only have this term, and what's left is VR plus IR cosine theta R. Sorry, VS is equal to VR plus IR cosine theta R IXL. Regrouping, we have VS equals VR plus I, quantity R cosine theta R plus XL sine theta R. So this is just the thing. Okay? Now, we have few things to take note. Okay? This approximate formula is quite accurate for normal range of flow, according to reference 1. Okay? Reference 2 said that it gives fairly correct results for lagging power factor. But for leading power factor, it's not it has appreciable error. Therefore, according to that reference, this approximate formula should be used only for lagging power factor loads only. Okay? So, the one given by this author, by this reference, the one for leading power factor, actually contradicts the theory of author 2 or reference 2. Okay? By the way, author 1 is DDAS, Electrical Power Systems, and author 2 is META, Principles of Power System. Now, so what should we do now? What should we use now? Okay? We may just rely on the complex or phasor notation because more or less that is sort of more accurate. Okay? That's our first resort. But if not, if it will make our solution or calculations more complex, then we can just make use of the approximate. Okay? So for the complex or phasor, simply use this. Okay? We just have to take note that the reference here is VR for this complex, okay, notation, whereas here the reference is I. But definitely this VS squared equals to VR blah 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 is just the same. Alright? So I would like you to try answering this. Okay? If you can still recall, this is quiz number 5, number 2, and number 3 that I told you not to answer anymore because it kind of require a concept that we just had discussed here. Okay, so again, try answering number 2 and number 3. I might have to ask you to submit that once classes resume next week. Let's see. All right. Okay, that would be all. Thank you and hope you learned something from this supplementary material. Bye.